Right, there you go. Ready to go? There you go, Cam.
70, I think. First and second. As well, so they're probably so used to it, really.
Oh, right. Oh, you could tell them for those, or?
Yeah, it's a cardboard.
Oh, right.
Okay, guys, should we make a start? I don't think it needs any introductions, so.
Any more introductions? Yeah, good morning, everyone. I thought we'd make a start almost on time today, because this workshop is, the beginning of it is going to kind of build on some of the things in the previous two. So if people come in a little bit late, then they hopefully won't miss so much. But it's probably quite a good idea to be reminded anyway. So this workshop wasn't designed to be part of the series with the other two. It's more of a standalone thing. But I think it's appropriate, and we discussed it, Paul and I, and we thought it was good if you had some awareness of going a little bit further than descriptive statistics. So this is what's called statistical testing. I think I talked about that 2 weeks ago when I was here last time. It's like the second step in statistical analysis, but we can't really do it on its own. So we're basing this workshop around a particular example to do with the Great North Run, which I'll introduce in a minute. So we're going to do some descriptives with that and then the testing, so that it's kind of a more integrated approach. And the whole approach is called quantitative data analysis, so that's why we've got this slightly convoluted title, including both ideas. Okay? All right so far? You look like you're about to say something. Okay.
Show us the time.
Keen student. Right, so what we're going to cover, I'm going to make some initial remarks. You've already done data types last week, but we haven't, I don't think you talked about analysis based on data types, so I'll move on to that. We talked a little bit about data preparation and the analysis process, so I'm going to go through that a bit more. Then we get on to this example from the Great North Run. We've got some descriptives we're going to use at the beginning: histogram, summary, scatter plots. And then we'll look at these particular tests called the paired t-test, the unpaired t-test, and correlation and regression. They're about the simplest tests that you can do in statistics, so they're a good place to start. And this data set, the way it's been constructed, allows you to do all of these types of tests. Okay, so far so good. So initial remarks. Well, this is more to do with this being a standalone workshop, I think.
Hello.
Morning. So maybe I'll skip this because I think I've covered some of this already. You're aware of this isn't like a standalone workshop. You've got a series, and you know it's not going as far as it might. So just forget about that. Before you analyse, I've talked about some of these issues already as well. Clarifying your research question: what exactly are you trying to investigate? Unless it's a kind of explorative analysis where you don't have a set hypothesis, you've got to watch out for what's called type 1 errors. Oh dear. Oh dear. That's a permanent marker. Not a permanent marker, it's by mistake.
One here.
Thank you. Let me just try and get this one through. As soon as I use it. Good job. Thank you. I'll have to get it. It's starting to work. You might need help. Type 1 errors. Type 1 errors are a problem when you do lots of tests. it's to do with this 95% cutoff I was talking about 2 weeks ago in statistical testing. So if you do lots of tests, you're increasing the probability of making a mistake. It's a bit like the court system. If you do lots of cases, then you're increasing the chance of convicting the innocent, unless you have a very high threshold of what they call beyond reasonable doubt conviction. So it's the same thing in statistics. So although the level is lower, so if you do lots of testing, then you can have a problem. So having a research question is a good idea if you can possibly do it. You need to design your experiment in terms of thinking about what variables you have and how you're going to analyze them. So you'll get a few examples in a minute based on this data set. The data collection method, I've suggested using different approaches if you're collecting data. Some students, when they're doing dissertations, they rely on online questionnaires, and then what happens, they get maybe 4 responses, and then they write their whole analysis, but it's completely meaningless because they don't have enough data. So sometimes it's good to be pragmatic about where you're getting your data from, to combine sources. And making sure your sample is representative and sufficient size. There aren't any hard and fast rules about size of data samples because it depends how big an effect you're trying to measure. If you're looking for, say you're looking at 2 groups, and if there is a big effect between those 2 groups, you may only need maybe 10 in each group, a bit like the one I'm going to show you in a minute. But if it's a very small effect, you might need 100 or 1,000 in each group so that you can actually identify that there is a difference between the groups. So that's the problem in statistics. You don't know how big a sample to take if you don't know how big an effect you're looking for in the first place. But it's important to have good quality in your data. Data types, I think Maggie talked about that last week, so I don't need to go over that again. But what I will do is show you this, this slide, which connects the data types with some things you can do with them. First of all, you've got the mathematical operations. So with nominal data, you can only count the data. But with ordinal data, you can count and also order the data. That's why it's got the less than, greater than sign. With scale data, you can also add and subtract. Now, the issue to do with multiplying and dividing as well, there are actually 2 subcategories of scale data. You don't have to worry about that in any analysis I've seen with any student at the university or member of staff. So I would just forget about that. The important difference in terms of adding and subtracting is that you're able to calculate things like a mean. Which, where is it written? This median mode. I've left the word, oh, here it is, mean. Yeah. Okay, you can't calculate means with category-based data. So that's a very important distinction. Because you're ordering ordinal data, you can calculate a median, because that's 50% of the way through the data. Also, I think, did Maggie talk about the upper and lower quartiles last time? So you've got that sort of thing here. So some people call this the famous 5, I think, in terms of summary statistics you can get from ordinal data. But you can do a lot more with scale-based data. So I'm going to talk about skewness and kurtosis today. They are 2 ways of measuring how a distribution of data is different from a normal distribution. So there are ways of combining 2 data series together. If it is scale data based on scale, it's called correlation. And we also get linear regression connected with correlation. correlation is looking for a linear association between two scale variables. If the data is category-based, you can either do the chi-squared test with a two-way table. I don't think I'm going to cover that today. It's quite a common thing with questionnaires, though. It wasn't suitable for this example set. And you can't do it in Excel. And that's the other thing to mention. There is another workshop I do which does all the analysis in this one in Excel. But because chi-squared is very fiddly in Excel, I've not included it in this workshop. But it is quite a common test. So it is something you might want to look at in addition to the tests I'm going to introduce this morning. So you can do a non-parametric correlation called Spearman with ordinal data. You can't do a linear one because it's based on only measuring which is higher or lower than another. It's not based on the actual value of the numbers. So again, I'm not going to cover that today, Spearman correlation. So the ones I am going to cover are the ones in red. So we'll get onto those in a minute. You get the idea. So you can either combine two series together, or you can look at two or more groups of data and maybe compare their means. Right, once you've collected your data, this is a very important stage. I don't know if you're doing any data collection and analysis, but it's worth being aware of this even if you aren't immediately going to use it. A lot of people aren't aware of this stage. They will do an online questionnaire like SurveyMonkey, and they'll get frequency distributions for individual questions out of it, and then they say, well, what shall I do next? And if they come to me, I say, well, if you've used SurveyMonkey, you're going to have to pay about £20, £25 to get the raw data out of it. Because what it's not telling you is how the answers in one question correlate with the answers on another question. It's just individual question output it gives you on the free version. There are some free systems or much cheaper systems you can use which give you the raw data. So I'd really advise against students using SurveyMonkey for that reason, even though it's maybe easy to use and popular. So what students need to do is to put their data in a form like the one I've shown you in these examples. So if you're planning to just use Excel, you can use text in terms of the data itself. So you've got the respondents going down in the rows, you've got the questions going along in the columns, and you've got the data in the rest of the sheet. And if it's Excel, then you can use text. If you're going to import it into a statistical package like SPSS, then it very much prefers numbers. I'm not saying there's absolute requirement for numbers. Sometimes it works with text as well, but it's really not worth getting into all the quirkiness of SPSS. I think certain tests work with text. So we recommend using numbers. So the number 2 here refers to a Y. The number 1 refers to an X. You get the idea. The 3 refers to 46 to 60. So what am I trying to say? The simpler descriptive statistics and maybe some of the statistical analysis can be carried out in Excel. But some students, because they maybe need to do a chi-squared test, that's why you have to pay £25 to SurveyMonkey and cry if you're trying to do a chi-squared, because you can't associate maybe here product choice with age group. It won't give you that for free. So that's why you would need to use something like chi-squared, and you couldn't really do that very easily in Excel. So it's better to use SPSS at that stage. So we recommend kind of starting off creating a data set. Both of these are created in Excel. They're like two separate sheets. within an Excel file. And then, if necessary, import the data into a statistical package and use that for the more sophisticated analysis. Anyone got any questions about that?
Yeah, I was just going to ask what SPSS. I'm presuming it's a statistics package, but
Yeah, it's a really powerful statistics package, which is the one. It's not so much available on this campus for some reason. There's a few rooms in Millennium Point which have it, open access rooms. But the other campuses, I think it's in all the open access rooms. So it's used across the university. So it's the most popular statistical analysis package. And there are certain things you cannot do in Excel, which when we get to them, I'll explain what they are.
The one called R.
Yes, R is, I think it's more, it's free for one thing,
Yeah.
but it's not menu-based. It's more kind of syntax-based. So it has that disadvantage. You can't use menus to select things.
Right,
you have
okay.
to write the script
Right, okay.
yourself. So it's a scripting language. Hello.
statistical.
Yes, welcome. There's a sheet to sign somewhere. Okay, so I've just gone through that. I think I've talked about that. Right, just have a look at this slide. So I think this is similar to the 7-step thing I showed previously in terms of the data analysis process. So it's a similar kind of list. So the basic idea is you do the descriptors first, you make an informal interpretation, and you combine that with your research questions, and you decide what you're going to focus on in more detail. Choose the right test, run the test, interpret it, but don't consider that to be a fait accompli. You may need to kind of retest, look at something else, use a different test slightly. It's a modelling process. There isn't a right answer most of the time. Maybe with a very simple data set you could say there is a right answer in terms of how to analyse it. Okay. Some common mistakes students make. Too small a sample size. I've talked about that already. The data is not randomly selected. It has some bias in it. It may not be possible to eliminate all bias, but it is something that should be taken into account in the way in which it's reported. Yes.
Isn't there's like also a quite simple formula like for the sample and then the you know the is it the error? Like the sample size. I didn't know about the.
But it's based on the effect size.
Yeah. Right. Okay.
We do have a series of more advanced workshops, and this is, I think this is in workshop 13 out of 15 sample size calculations, and there are some online tools which do it for you, but you have to say how big the effect size is. And effect sizes, they're either small. Oh, is that pen? Oh dear, I'm not having a very good morning with pens, am I? When I did the one, or creating a problem for someone else, and I got to head off straight afterwards. They're either small, medium, or large, would you believe? And it's to do with the way, I think you look at the difference in the means of two groups. Can I use, am I going to scare you if I put that? Or a mean, x bar 1 minus x bar 2, even this pen doesn't work, so I don't scare you too much. You take the absolute value of that and you divide by the standard deviation of both groups. That gives you a number. That's called effect size. There are different ways of measuring effect sizes. And you need that in order to, that's what, the effect sizes are either small, medium or large, and based on that, and based on the test, it will tell you how big your sample should be in order to minimize not type 1 errors, but what's called type 2 errors, which are acquitting the innocent. Acquitting the guilty rather than convicting the innocent. So that's where sample size calculations come in. But that is more advanced material. So we would just say, try to avoid bias and look in more common sense ways about it. Okay. So when students write things up, they don't talk about how they collected the data. The answer categories in their questionnaires might be a bit vague or inconsistent in some way. Maybe they overlap or they don't cover all possible cases. I've talked about this issue of cross-tabulation, how important this is, and how you really need to use a statistical package and get the raw data set out of, if you're doing an online survey. And then finally, students who copy and paste the output from statistical software straight into their report without interpreting it. We do recommend, if you want, you can put it in an appendix, but it's about identifying what parts of the output are telling you something and what they mean, rather than just putting the whole thing in without any write-up to go with it. Okay, this was a colleague actually from Lenin Point who gave me this list after many years of woe looking at student dissertations. I said I will include it in my workshop. Okay, so on to the example data set. Do most people know what the Great North Run is? It's the biggest half marathon in the UK. Takes place, I think is it around Easter time or? No, it's not Easter, that's the London Marathon. I can't remember when it is, but sometime in the year, every year. It's about 50,000 people are involved in it. Now it's really grown over the years. So one particular year, what happened was 11 runners were requested to give a small blood sample at the beginning and the end of the race in order to measure their what's called beta endorphin concentrations, which is the body's natural painkiller. So the assumption is when you do exercise, the endorphin levels go up. And then another 11 runners who had collapsed, but their conditions were not life-threatening, were politely requested if they would give a small blood sample, and they agreed. I don't know how many were asked. 11 agreed. That's the data from them as well. So you've got the collapse runners in the third column. So as I've already said, this is a small data set, but we're looking at quite large effects. So obviously if I'd put a lot of data here, it would have been difficult to take in the numbers. But you can generally see that the after values are bigger than the before values, and the collapse values are even higher. So people who collapsed were struggling, and their body was creating more endorphins than even the people who run normally. So they collapsed near the end of the race. Okay, so something a bit misleading with this table is the way in which the three columns are put together, because these are the same people here going across. These are in ascending order. I think, yeah, like it goes 24. You can see these are not in ascending order because this data is what's called paired. It's the same people being measured twice, and that's a very important concept in statistical testing. Has the data been measured twice? In fact, I had a member of staff come to me last week who collected, I think, 250 questionnaires from students that she'd been teaching, and she was going to collect a similar number at the end of this term. And I said to her, it looks like these questionnaires are anonymous. And she said, yes. And I said, well, you're looking to measure an effect, how are you going to pair up the people from before and after? And she said, oh dear. So she completely messed up the design because she hadn't realised that she was actually looking at paired data, but because she'd anonymised the questionnaires, she couldn't work out who had done it before and after. That was a major problem. So this data here is 11 different people. So really, we shouldn't put it in the same table. So that's a bit misleading. We've got 3 research questions. Firstly, does running, so this is to do with the before and after measurements, does running increase your endorphin concentration levels? Do people who collapse at the end of the race have higher endorphin concentrations than those who run and don't? And is there an association between your values before and after? Just to go back, maybe you didn't quite look at that. These values here, you know, they're around 20, but here there's kind of 20 to 40-ish. So it looks like there's a bit of an association between the before and after values. It's not so clear. We're going to produce a scatter plot in a minute to kind of visually represent that and think about it. Okay, so as I've already said, it's better to present the data like this rather than as a single table. So we've got runners with IDs 1 to 11 before and after. That's what's called paired data. Then we've got an independent set with a different ID number, which is the people who collapsed at the end of the race. Everyone happy with that so far? So that's really important stage in interpreting the data. So we're going to do a bit of descriptives and initial analysis first. So I'm going to talk about the normal distribution and then look at histograms, some summary statistics, and then a scatter plot. I presume most of you have seen the normal distribution before. It's the most common curve for a probability distribution in statistics. I think we covered this a bit, didn't we, 2 weeks ago in terms of the coin tossing. So when you toss a coin a lot of times, the probability of all the different outcomes in terms of the number of heads, it turns into a curve which becomes more and more like this curve. So a lot of experiments have that nature to them. So it's not the only curve you can have, but it is a very common one, and we use it kind of to get the concept over of a parametric test. The parametric tests are based on assuming that data comes from a distribution of some sort. So the normal distribution has a mean value and a standard deviation. So if the mean value was to change, then the whole curve would move one way or the other. If the standard deviation was to change, then it would get wider or narrower. But essentially, it's the same curve. It's just changed its dimensions, the same shape, essentially. Okay, so I'm going to talk about that a bit more later on in terms of these numbers and those percentages. So what we can do is create a histogram. You did that last week, those of you who were here. So looking at the frequency for different intervals for the concentration, this is the before group. And we call this data skewed because it seems to be kind of the whole distribution is pushed to the left compared with the normal distribution. So when the data is pushed to the left, it's known as a positive skew, which is a bit weird. You'd think it would be negative because it's negative numbers are to the left, but that's just the way it is. I didn't invent this. So there seems to be a possible problem with assuming that this data is normally distributed. So we're at the stage of informally assessing these assumptions at the moment. If we're going to run a test which is based on the assumption the data is normally distributed. People got the idea of what's going on. I've shown you the normal distribution curve. Now I'm showing you the histogram, and I'm talking about how the histogram isn't really, there might be a problem with it having such a high frequency on the left. The after one looks all right. It's got a peak in the middle. The interval values are higher than the before ones. The before ones, they went up to 20 or 18. Here they're going up to 50. So it's just bigger values, really, it's measuring. And then the collapse values, there's one which is way off the end of the scale. So last week you did box and whisker plots? Yeah? If we were to do a box and whisker plot, and again, I've not done it today because it's almost impossible to do them in Excel. It's not something I recommend. That value on the right would be an extreme outlier. So Maggie talked about outliers and extreme outliers. So outliers are okay. Maybe they're a bit of a problem with such a small data set. Maybe once you've got about 20, if you have one outlier, it's all right. But an extreme outlier is a big problem, I think, with such a small data set. So that's telling us there is a big problem to do with the assumption of normality for this particular group. So that would indicate maybe we shouldn't be running a parametric test. Are you getting me? It's a bit of a, you have to go through this process of deciding whether a parametric test is appropriate or not before you run the test. Okay. Some more concepts, skewness and kurtosis. I've mentioned skewness already. You can think of it to do with pushing the curve, the histogram curve, to the left or to the right. That's all you need to know about it. Kurtosis is to do with the size of the peak in the middle of the data set. So if it is a lot more peak than the normal distribution, which has 0 kurtosis, then it has a positive kurtosis, and if it's flatter, then it has a negative kurtosis. So the normal distribution has 0 skewness and kurtosis. So you can calculate these in Excel. The trouble is, you don't know whether the numbers are significant or not. I can use that word, I think, statistical significance. So here's the summary statistics of the groups. So you covered things like mean, median, range, standard deviation last week. So I've added skewness and kurtosis at the bottom here, and I've circled these ones for the collapse group, because these numbers are really quite high. So the kurtosis is very high for the collapse group, meaning it has a big peak, and that's because of that number right, that extreme outlier. If that extreme outlier wasn't there, the whole distribution would have changed shape, and it would have been much lower, basically. But you can't just remove an outlier because it's an outlier. This is what some of our friends recommend in one of the departments. You're not going to sue me, are you, Paul, about that?
No. I was just going to say there is a function in Excel to calculate skew.
Yeah, skewness and kurtosis is in Excel. That's why I've included it. But what you can't do is measure what's known as their standard error. So the larger your data set is, the more accurate your estimates are of all of these things. So with each of these estimates comes a standard error to say, you know, how sure are you that it's this value? With the mean, it's actually very important, the standard error, because it creates what's called the confidence interval. Not that you can read it very well. Confidence interval. So when you are reading a scientific paper, confidence intervals is a very important concept. If they talk about these, then it's a good paper, generally speaking. If they don't, then it's not so good. So they are measuring the degree of error in terms of the estimate of the mean, because it's the mean based on your sample rather than the mean of the entire population. So the entire population here is everyone who ran the Great North Run, or everyone who collapsed at the end of the run. The mean is only calculated based on the ones we measured. So that's why there has to be some degree of, being uncertain. But the more people you test, the more accurate your estimate is. That's why people do opinion polls with a few thousand, excuse me, a few thousand people, because then they are fairly confident about the values. In fact, they're confident within certain thresholds if you read the small print. So that's why they use that size of sample. Because if you have a smaller sample, you're less confident with the estimates. Have I totally confused you now? Have you managed? Yes.
So, you know the skewness in the curves, like, I mean, 7.42
Yes.
is nothing to me because I don't know
Oh,
how
right.
big a large number is. in
Well,
relation.
the problem is it's a small sample size. If it was like a sample of 100
Yeah.
and it had these numbers, then I would definitely say that data is not normally distributed. But because the sample size is small, you really need to know the standard error. That's where I went on this long digression. And you cannot calculate it in Excel, but it is given in a package like SPSS. It gives you both the estimate of these parameters and their standard errors as well. So then you can see whether they're important. And the rule is to do with the normal distribution, actually. If you just write it as it has to be so like the skewness is the absolute value of it is less than 2 times the standard error. The same for kurtosis. But this is the detail I was not. Why am I talking about this? Because you're limited in terms of what you can do in Excel. That's what I'm trying to put across. In terms of the assumption checking, before knowing whether it's appropriate to run a parametric test.
If you've got the normal, if you're assuming it's a normal distribution curve and you're using the thing that we've just done there, looking through the kind of histograms like the data.
Yes, yes.
What you're in effect looking for then is to see if the shape of the data that you've got pretty much shows a
Yes,
normal distribution.
exactly.
And if it does, then you can be fairly confident that you can
Yes.
and use the.
Yeah, so Paul is giving you a link on Moodle to our iCity page, which includes a worksheet which talks about normality testing, and that is one of the main things it talks about. Yeah. Okay, so these numbers look like they're a bit of a problem to me. Here's a scatter plot. I remember we were talking about that earlier. The lower values are a bit mixed up, but the higher ones seem to be maybe becoming more of a straight line. So there seems to be some relationship going on here, but is it a linear relationship? Is it statistically significant? That's what we need to work out. Okay, so the next stage is selecting and carrying out the right test. So I'm going to talk about the things on the slide here. Null and alternative hypothesis. I think we've covered some of these already, actually. I don't think I went through quite so much detail. Anyway, I think I'm just going to jump into this now, rather than read these out, because that's just going to confuse you more. So the null and alternative hypothesis, as I've mentioned before, I think the best way of thinking about this is the scenario of a court and the assumption of innocence being the place at which you start. So in nearly all countries in the world, you assume someone is innocent until proved guilty, or not exactly proved, but a judgment is made beyond reasonable doubt. So the assumption of innocence is known as the null hypothesis in statistics, or it's written H0. And the aim of statistical testing is to, you could say the aim is to try and reject that null hypothesis with a certain level of confidence. Well, you're trying to make a decision, the right decision based on the data presented. So the level of confidence has to be at least 95%. And the opposite to the null hypothesis is known as the alternative hypothesis. So if you're going to reject the null hypothesis, you're going to accept the alternative hypothesis. Any questions about that? Everyone happy so far? It sounds a bit peculiar the way it's set up, but that's just how it is. You just have to get used to it. Here's a table which talks about the different levels of significance. There's 3 main levels. It starts at 95% and goes up to 99.9%. So they are the bottom 3 rows of the table. The top row is where there is nothing going on in your data set, and you're going to retain the null hypothesis or not reject it, and you don't have any evidence to reject it. So maybe we could just look at the middle row in a bit more detail. The way you make this decision is based on the probability value of the test statistic. But this is nearly always we run a certain test, it has a statistic to do with the test, and then it has an associated probability value. So in that middle row, we're looking at the value between 0.05 and 0.01. So if you think about the normal distribution, which I think is on the next slide, it's about being in the tail of this distribution, either between here and here, or between here and here. So the statistic value is the value along the horizontal, the x-axis, or sometimes with z, I think, with this, yes, with z there. So that's the statistic value, and then the probability value is measuring the area under the curve from whatever value you've got. Say it's 2, then it's going to be the area on that side going towards infinity, and the area for the opposite side from -2 going towards -infinity. So the number 0.05 is to do with this cutoff value 1.96. There's 5% of the area under the curve is in these 2 tails, measured by 1.96 and -1.96. Alternatively, 95% of the area is inside this main part of the curve. So you may have seen that before in statistics, but not realized how it's connected with statistical testing. So this is what's called two-tailed testing. And in the first workshop, I talked about tossing a coin 20 times, and a significant event was one where we had at least, was it 15 heads, or at least 15 tails. Well, that's almost exactly the same idea, it's just different numbers, because that gave us a probability value which was with an area associated which was less than 0.05. I'm getting some positive facial feedback. A little bit concerning. Anyone like to say something? It's quite conceptual, but it's also very important. I mean, I've tutored third-year psychology students who are supposed to know all this before they start their degrees, and they said to me, oh, if only someone had explained this at the beginning of my course. So it's worth trying to get your head round. There is something called CAST. I think I might have mentioned it last time. Which is our Java-based set of simulations to do with statistics. The link is on these slides, and I think it's on the iCity site as well. And that's a really good way of getting a better feel for these statistical concepts. But I don't have time for that today. Okay, so going back, I was talking about the middle row here. So I've explained what it means in terms of the normal distribution for this number to be 2.05.01. So what you would do is you have a formal action and an informal interpretation to go with it. So the formal action is you're going to reject the null hypothesis at 95% confidence. And you would talk about evidence to reject it. So then, the further you go down the table, the stronger your evidence is, and the higher your level of confidence in rejecting the null hypothesis. But I should emphasize that statistics is very different from mathematics. You're not proving anything, you're just making a decision beyond reasonable doubt. So, example might be climate change. It's now, I think it's moved, this World Summit of international scientists have moved their combined level of significance from 95% to 99 or something. Or the Higgs boson, another one, that's like 99.999% sure that it exists. That's why they've said it exists, because this spike they're getting in their energy levels seems very unlikely to be a random effect because of all the data they've collected. To get the idea. So the tricky one is this one here. This is kind of the liminal space in between significance and non-significance. So formally, you retain the null hypothesis. You don't reject it because the probability value is too high, but you can still report on it informally as being weak evidence to reject it. Okay, so in statistical testing we use this table again and again. So it's important to get the idea of it. Right, so I've talked about that one. Most tests are two-tailed rather than one-tailed, because you don't make an assumption about what way the data you have is different from random data. You're not saying it is one way or the other. Like the tossing a coin, we weren't saying that it was biased towards heads necessarily, even though we stuck the blue tack on the head side. It might have been, we didn't have any prior assumption. So that's very often the case. I would always use a two-tailed test unless there was a very strong reason to use a one-tailed test. Okay, so with remember our three research questions, we can formulate them as things that we're trying to show, which are three different alternative hypotheses. So these are the opposite to the null hypothesis. So the first one is that before and after concentrations come from different random samples. So the run has had an effect. Secondly, the collapse runners and after runners are from different random samples, meaning collapsing at the end of the race has an effect. And thirdly, that there is a linear correlation between before and after. These are the things we're trying to show, but we have to assume the opposite in order to test it.
Just for me, can you just remind me what the null hypothesis was for me?
Well, it'll be different in each case. So the first one, it'll be the logical opposite of that statement. So the logical opposite is that before and after concentrations are from the same random sample, meaning the run has had no effect on the concentration
The
levels.
difference is what you're hoping to look at.
Yes, you're hoping to show. Yeah.
And when you interpret into the reality, it means that the ones who were tested before and after are good runner, and the other ones are kind of amateur or something.
I missed the beginning of that.
I'm
Sorry.
trying to understand when you interpret the statistic into the reality, what does it mean?
Right.
Because the one who collapsed
right.
at the end.
Collapsing means your body's natural painkiller has gone through the roof
Okay.
because you've really struggled physically. So your body has created a lot more endorphin than people who just ran 13 miles and didn't collapse.
Okay.
Yeah, that's what it means.
They are in bad shape.
Yeah, they're in bad shape. in terms of concentration. Okay, so we come on to a little table now in terms of which test to choose, which I'm going to repeat. So this is quite a useful slide in terms of test selection. So you've got the data type in the first column, nominal, ordinal, scale again. And then you can either look for a combination of two variables, or you can look at the difference between two groups. So it's one variable with two groups. So at the moment, this first test, which is the before and after, it's the same people being tested twice. It's scale-based data, and you're comparing those two groups of data. So we're definitely in this part. It's scale-based, so we're in this row, and then we have to choose between these. Is it related or unrelated? Well, it's going to be related because it's the same people being tested twice. So that's what's known as the paired samples t-test, which is a parametric test. It should only be used when its assumptions are satisfied. Otherwise, the equivalent non-parametric test, which is called Wilcoxon, should be used. So you get the idea of how to interpret this table. We're going to run the paired samples t-test, a little bit of information about it. So I've talked about this already. It's the same people. So it's looking at the difference in means between paired data. It's the before and after levels. And because it's paired, we can turn it into a single variable, after minus before, for the concentration levels. So the test assumes that data is normally distributed. But it does work in other circumstances. Again, I can't really go into the detail of it now. I'm now confusing you even further by saying the data doesn't have to be normally distributed for the test to work. So when I talk about this, I give a picture of a kitten in a shoe. Because I've got this wonderful picture I got off the internet of a kitten sleeping inside a slipper. And the kitten represents the data, and the slipper represents the parametric test. So, you know, the slipper was not designed for kittens, but it works very well with kittens. So sometimes parametric tests, they work with different data sets to the ones that they were designed to take. So that's another whole area of complexity. So that's where I'm using the word robust. So if you want more information about that, you have to look in the more detailed workshops. So again, we've only got the sputum symptosis values here rather than their normal, their standard errors. So you can only do so much in Excel. So when we run the test in Excel, we get this as the output. Just to mention, in case you want to do it yourself, you have to create something called a data analysis button on the data tab in Excel, and you have to do that going into the properties. I'm not sure how you would do it on these Macs. I know how to do it on the PC version of Excel, but I think it's slightly different on the Macs. So otherwise it's not available. It's one of these tool packs you have to load. to get all these tests in Excel. But it's explained in another workshop. So it gives you this output. So you wouldn't copy and paste this straight into a report. You would need to interpret it. You might put it in an appendix. So the important number is this number here, which is the probability value of the two-tailed test. As I've said, normally we use two-tailed tests. We don't assume that the data is one way and try to prove that. So this number is very small. If you remember, the numbers we were looking at for the probability values were less than 0.05, less than 0.01, or less than 0.001. So this one was lower than the lowest of those. So that's very good news in terms of the alternative hypothesis. So we've got very strong evidence that running does increase beta endorphin, or it has an effect at least. It wouldn't necessarily say it increases based on having a two-tailed test. It's definitely having an effect. Okay, the second one, this is where we're looking at the after values and the collapsed values now. So it's the people who collapsed at the end of the race, measuring them in good shape, and another 11 people are still jogging on the spot, being very happy, having just given their second blood sample. So which test did we use? Well, it's now unrelated. It's still scale-based and we're comparing two groups, but that's why we're using the independent samples t-test. Although for this particular data, there seemed to be a big problem with that outlier, which may have affected the results. So I'm just going to run this test as to show you how the test runs, rather than it being the appropriate test with our particular data set. I think this ManWhitney test would probably be a better one to use here with this particular data, but again, you can't do that in Excel. So again, I'm showing you sometimes you need to use a more sophisticated package. This is part of the purpose of this workshop. Okay, so the unpaired t-test is pretty similar. It's just you can't create a variable where you combine these together because they're different people. So you can't say after minus collapse or collapse minus after. It doesn't have a meaning. They have different ID numbers, if you remember those two tables we had. So it assumes the data is normally distributed for both variables, both the after and the collapse. There was a problem with ours. And there are two variants of the test, and a little bit more complexity to it. So it's to do with the standard deviation, or the variance of the two groups. So in one version it assumes that they're the same, in the other version it assumes that they're different. And you need to test for that first. So in SPSS there is a test for that. In Excel there isn't. You need to use a rule of thumb, and the rule of thumb is that the ratio of the variances is less than 4 to 1. I'm just going to show you that on the output of the next one. Here's the output. So we've got the means and the variances of the after and collapse groups. And the variances, this one's about 10,000, that one's just under 100. So the ratio is about 100 to 1. So it's much bigger than 4 to 1. So that's why I have run this version of it in Excel, assuming unequal variances. So there are two versions of the test in Excel, assuming equal variances and assuming unequal variances. So you need to get the variances first, work those out first, and then decide which variant of the test to use. Okay, so I'm using the right version of the unpaired t-test, two-sample t-test, and then you can interpret the probability value. So even though the means are in the ratio, is it about 5 to 1, and the previous ones were, I think the ratio was less. Where is it? Here. They're in the ratio about 3 to 1. Now you can see there's a difference in these tests because the probability value is higher and the level of confidence in the decision is lower. So we're no longer having very strong evidence, we have strong evidence. And instead of being 99.9% sure, we're only 99% sure. So what that's showing us is that the paired t-test is a better test than the unpaired t-test. Yeah? So think about my colleague who came for the tutorial last week and had randomized her data and wanted to look for an effect. Do you see what influence that's having on the testing? So if you don't pair the data up when you should, you can lose statistical significance. Okay, so the conclusion is that collapsing at the end of the race is different from just finishing the race normally. They are from different samples. But we're only 99% sure now, rather than 99.9. The third one is we're now looking, remember at the before and after values, to look for a linear association between them, or correlation. So we're now in this column, scale-based data is looking at these now. So we do these two things together. The Pearson correlation, which is going to give us a number, a correlation coefficient, and the linear regression, which is going to fit a best fit line, straight line, to the data. So they go together. And I'll just talk about the Pearson correlation first. It's not a measure of the slope of the fitted line, it's a measure of the alignment of the points. So we start by looking at these two pictures here. You see these are perfectly aligned. So this one has a Pearson correlation of +1 because the line is increasing. This one has a Pearson correlation of -1 because it's decreasing, but they have different slopes. So you need to kind of get away from the concept of it being to do with the slope of the line. The other ones are kind of in between. So 0.7, they're fairly aligned positively, -0.7 fairly aligned negatively. The others are more scattered. Okay. With the CAST website I was mentioning, there is this very nice interactive graphic for getting a feel for what linear regression is and least squares linear regression. So this is based on a number of data points given by these little X's here and a fitted line, which you can actually move yourself, and it's creating these blue squares. So it's measuring the vertical distance of the points from the line, and then it's squaring that and creating a square with a certain area, and then it's adding these areas together. This is what it's called the sum of the square of the residuals. So as you move the line using these little things up and down, it's going to change the size of the squares, and then the sum of those areas is going to change. So it's like a game, you're trying to make that as small as possible. And that is what least squares fitting does. It finds the line which minimizes the sum of these areas of these blue squares. Okay? you want to have a go at it, you can. You need a machine with Java, and I didn't try it on this one, just in case it didn't work. So any machine with Java on it should run. You can test it out. Right. Some slightly good news in terms of assumption checking. It's much easier with correlation and regression than with the t-tests. The assumption checking you can do informally just using your eye. And it's what we call a cigar-shaped scatter plot. So I don't know if this looks rather a fat cigar here. But mathematically, it's an ellipse which is rotated on its side. And it needs to cover most of the points in the scatter plot. So we've just got this one point outside, which you could worry about a bit. But if there isn't a linear relationship, it's a problem. And if the scatter plot is fatter at one end and thinner at the other, in fact this does look a bit fatter here and thinner at this end. But this one, I don't know if I would recommend using correlation and regression or not. It's a small sample, so you can probably get away with it. You can get away with more things with a small sample. You need a linear relationship, and you need it to be the same width at one end as at the other end. So that is all the assumptions for Pearson correlation and linear regression. So you can just look at the scatter plot and make a decision based around that. So when you run it in Excel, you get an output like this. So this is the output from the regression, and it includes the correlation. So this is why I talk about them together, because correlation is like a subcomponent of linear regression. So just to interpret it, correlation coefficient is 0.5 here, which is, I think that's, okay. Sure. So remember small, medium, large earlier? Well, here, the Pearson correlation, the values, according to someone called Cohen, are 0.5, 0.3, 0.1. So that's how you would interpret a correlation coefficient of 0.5. We'd say it's a strong relationship, but it's not a significant one. It's not significantly different from 0 because of this probability value given here is bigger than 0.05. So it could just be a random effect to do with, because it's such a small sample, seems to have a strong relationship, but it could be a random thing. So if you had a much bigger data set, you should find that the probability value is going to go down if there is a relationship. So even with a smaller coefficient, you might get a much lower probability value. Like those pictures of 0.7 I showed you, they were much better. I think the 0.7 and minus 0.7, they would have had a much lower value. Right. And then it also gives us the fitted line here. So we get the constant and the slope are what it calls the intercept, and then it just gives you the name of the variable before. So you can then plot that on the scatter plot. So those numbers, 17.2 is it, and 1 point something, they correspond to the fitted straight line on the scatter plot, the best line. So if you think about that picture I showed you before from CAST, and those blue squares, imagine them being on here, that would be the best fit for this data set. But because the probability value of the slope is a bit high, then maybe you shouldn't plot it. Don't worry about this one, even if it's not significant. We tend to plot that line even when that's not significant. But it tells you what the best fit line is. Okay. So hopefully I've got you thinking about things in the right way now. So you've got these parametric tools which you can use to analyze data sets, but you've got to do it carefully. You've got to decide whether you should be using them, and then you've got to interpret the outputs in the right way. So just to summarize, garbage in, garbage out. Make sure you've got a good data set to start with if it's all possible. Need to do a preliminary analysis, which is your descriptives, where you present and describe the data, make initial hypotheses based on your research questions, choose the right test its assumptions if it's parametric. If it's non-parametric, then there aren't any assumptions, so you don't have to do that stage. Then you carry out the test, look for significance, interpret the results. And don't just create graphs and software printouts, you need to write a commentary to go with it. Good. So, just a few links. I've talked about these workshops. What I covered today is based on workshops, I don't know about 9. 9 is the non-parametric. I've covered 7, 8 and 11, definitely. I mentioned 13, which is the thing to do with sample size calculations. CAST, I've talked about already. Stats Tutor is like a different approach to CAST. CAST is electronic books based around simulations. Stats Tutor is kind of much smaller resources in different media, looking at particular issues. So we've just made a donation of about 30 resources to Stats Tutor. Sort of worksheets and presentations like this one. So it's a national repository based at Loughborough University. And then there are some books in the library. So you can get this from the slides. And we do appointments if you want to come and see us, either for 30 or 60 minutes. So Maggie, who you've met, is based in Millennium Point. I think she tends to cover, which is fine with the descriptives. She might do simple statistical testing, but she won't go so far. Once you get to a certain point, she'll refer people to myself. I also have a colleague called Anil who can help at Millennium Point. That's about it. Any questions? I hope that's been useful to you. Yes.
Are there like other classes that are like the workshop? Are those just online?
The next time we're going to run the workshops is in the autumn.